Good day everyone, we are the Group 1 and welcome to today's lesson. In this video, we are going to discuss about the Markov chain. A Russian mathematician named Andrei Markov studied Markov chain in the early 20th century, publishing his first paper on the topic in 1906. Markov chain in continuous time were discovered long before Andrei Markov's work in the early 20th century in the form of the Poisson process. Markov was interested in studying an extension of independent random sequences motivated by a disagreement with Pavel Nekrasov, who claimed independence was necessary for the weak law of large numbers to hold. A Markov chain is a mathematical system that experiences change from one state to another according to certain probabilistic rules. The defining characteristics of a Markov chain is that no matter how the process arrived at its present state, the possible future states are fixed. In other words, the probability of transitioning to any particular state is dependent solely on the current state and time elapsed. The state spaces or set of all possible states can be anything, from letters, numbers, weather conditions, baseball scores, or stock performances. The changes of state of the system are called transitions. The probabilities associated with various state changes are called transition probabilities. The process is characterized by the state space, a transition matrix describing the probabilities of particular transitions, and an initial state across the state space. By convention, we assume all possible states and transitions have been included in the definition of the process. So there is always a next state and the process does not terminate.
Markov chain properties or characterizations. The idea is not to go deeply into mathematical details but more to give an overview of what are the points of interest that need to be studied when using Markov chains. The first one is reducibility, periodicity, transience, and recurrence. First, we say that a Markov chain is irreducible if it is possible to reach any state from any other state, not necessarily in a single time step. If the state space is finite and the chain can be represented by a graph, then we can say that a graph of an irreducible Markov chain is strongly connected, or which we call is the graph theory. So here we have the illustration of the irreducibility property. The chain on the left is not irreducible. From 3 or 4 we can't reach 1 or 2. So the chain on the right, or the one edge has been added, is irreducible. So each state can be reached from any other state. Second is the illustration of the periodicity property. So the chain on the left is 2 periodic. When leaving any state, it always takes a multiple of 2 steps to come back to it. So the chain on the right is 3 periodic. So third is the illustration of the recurrence or transience property. So the chain on the left is such that 1, 2, and 3 are transient. When leaving these points, we can't be absolutely sure that we will come back to them. And 3 periodic, whereas 4 and 5 are recurrent. So when leaving these points, we are absolutely sure that we will come back to them at some time. And 2 periodic. The chain on the right has one more edge that makes the full chain recurrent and aperiodic. So second is stationary distribution, limiting behavior, and ergodicity. So a stationary probability distribution is then such that it doesn't evolve through time. If the chain is recurrent positive, so that there exists a stationary distribution, and aperiodic then no matter what the initial probabilities are. The probability distribution of the chain converges when time steps goes to infinity. The chain is said to have a limiting distribution that is nothing else than the stationary distribution. Finally, ergodicity is another interesting property related to the behavior of a Markov chain. If a Markov chain is irreducible, then we can also say that this chain is ergodic. So as it verifies the following ergodic theorem. So assume that we have an application of f of x that goes from the state. So we can define the mean value that takes this application along a given trajectory or the temporal mean.
Now we have discussed the properties of Markov chain. Now let's tackle the types of Markov chain. To start off, we have Markov model. So a Markov model is a stochastic method for randomly changing systems where it is assumed that future states do not depend on past states. This model shows all possible states as well as the transitions, rate of transitions, and probabilities between them. So Markov models are often used to model the probabilities of different states and the rates of transitions among them. So the method is generally used to model systems. So Markov models can be also used to recognize patterns, make predictions, and to learn the statistics of sequential data. In mathematics, the Bernoulli scheme or Bernoulli shift is a generalization of the Bernoulli process to more than two possible outcomes. So Bernoulli schemes appear naturally in symbolic dynamics and are thus important in the study of dynamical systems, such as axiom A systems. So this is essentially the Markov partition. The term shift is in reference to the shift operator, which may be used to study Bernoulli schemes. The Ornstein isomorphism theorem shows that Bernoulli shifts are isomorphic when their entropy is equal. Subshifts of finite type are used to model dynamical systems, and in particular are the objects of study in symbolic dynamics and ergodic theory. They also describe the set of all possible sequences executed by a finite state machine. So the most widely studied shift spaces are the subshifts of finite type. So a subshift of finite type is called transitive if G is strongly connected. There is a sequence of edges from any one vertex to any other vertex. This precisely transitive subshifts of finite type which corresponds to dynamical systems with orbits that are dense. So an important special case is the full edge shift. It has a graph with an edge that connects every vertex to every other vertex. That is, all of the entries of the adjacency matrix are full. So it corresponds to the Bernoulli scheme without the measure.
Examples of Markov chain. First, board games played with dice, a game of snakes and ladders, or any other game whose moves are determined entirely by dice is a Markov chain. Indeed, an absorbing Markov chain. This is contrast to card games such as blackjack, where the cards represent a memory of the past moves. To see the difference, consider the probability for a certain event in the game. In the above-mentioned dice games, the only thing that matters is the current state of the board. The next state of the board depends on the current state, and the next roll of the dice, it depends on how things got to their current state. Such as blackjack, a player can gain an advantage by remembering which cards have already been shown, and hence, which cards are no longer in the deck. So, the next state or hand of the game is not independent of the past states. Number 2, gambling. Suppose that you start with $10 and you wager $1 on an ending pair, coin toss indefinitely or until you lose all of your money. If xn represents the number of dollars you have after n tosses with xo equals 10, then the sequence is a Markov process. If I know that you have $12 now, then it would be expected that with even odds, you will either have $11 or $13 after the next toss. This guess is not improved by the added knowledge that you started with $10, then went up to $11, down to $10, up to $11, and then to $12. The fact that the guess is not improved by the knowledge of earlier tosses showcases the Markov property, the memoryless property of a stochastic process.
So, good day everyone. I am Noel S, and after discussing you the introduction, the definition, different types, and of course the properties, and given the examples of Markov chain, I expect that you are already familiarized with the topic. So right now, at this point of time, I'm going to discuss the application of Markov chain, and we will solve some sample problems regarding Marcov chain. So assume there is a restaurant that serves only 3 types of food: hamburger, pizza, and hot dogs. But they follow a weird rule. On any given day, they serve only one of these 3 items. And it depends on what they had served yesterday. So in other words, there's a way to predict what they will serve tomorrow if you know what they are serving today. So for example, there's a 60% chance that tomorrow will be a pizza day, given that today is a hamburger day. So I'm gonna represent it in a diagram as weighted arrows. The arrow originates from the current state and points to the future state. I'm using the term state because that's the convention. So let's see another one. There's a 20% chance that tomorrow, again, they will serve hamburgers, and that is represented as a self-pointing arrows. Well, each arrow is called a transition from one state to another. Now, I'm gonna show you all the possible transitions. The diagram you are seeing right now is actually a Markov chain. Yes, the concept is simple as that. Now let us discuss some properties of the Markov chain. Well, the most important property of the Markov chain is that the future state depends only on the current state, not on the steps before. Mathematically, we can say that the probability of n plus 1 x steps will be x depends only on the nth step, not the complete sequence of steps that came before n. So at first glance, this might not seem so impressive, but on a closer look, we can see that this property makes our life a lot easier while we tackle some complicated real-world problems. Let's understand it a little bit. Okay, suppose the restaurant served pizza on the first day, hamburger on the second day, and again, pizza on the third day. Now, what is the probability that they will serve hot dogs on the fourth day? Well, we just need to look at the third day, and it turns out to be 0.7. So this is the heart of Markov chain, and it's known as the Markov properties. And the second important property is that the sum of the weights of the outgoing arrows from any states is equal to 1. This has to be true because they represent probabilities. And for probabilities to make sense, they must add up to 1. Here I should probably tell you that there are certain Markov chains with special properties. Now that you know what Markov chain actually is, let's explore our Markov chain by doing a random walk along the chain. So initially, we are on a hamburger day. So now let's see what they will serve in 10 consecutive days. So after 10 steps, we have situation like this. Now we are going to find what is the probability corresponding to each of the food items, aka the probability distribution of the states. Well, it's pretty simple. Just divide the number of occurrences of the item by the total number of days. For hamburger, it's 4 upon 10. For pizza, it's 2 upon 10. And it's 4 upon 10 for hot dogs. It's obvious that if we change the number of steps, then these probabilities will vary. But we are interested in what happens in the long run. Do these probabilities converge to fixed values, or they continue to change forever? So I wrote a Python script to simulate the random walk for 100,000 steps. I found that the probability converged to these values. And this probability distribution has a special name, which is the stationary distribution or the equilibrium state. This simply means that this probability distribution doesn't change with the time of the Markov chain. So we have managed to find the stationary state, but this method doesn't seem to be efficient, is it? Moreover, we don't know if there exists any other stationary states. Well, a better way to approach this problem is linear algebra. Let me show you. So first of all, let us think about how we can represent this Markov chain more efficiently. So this is essentially a directed graph. So we can represent it by an adjacency matrix. The elements in the matrix just denote the weight of the edge connecting the two corresponding vertices. For example, the element in the second row and the first column denotes the weight or the transition probability from pizza to hamburger. If an element is 0, then it just means that there's no edge between the two vertices. This matrix has also called transition matrix. Let's denote it by A. Remember that our goal is to find the probabilities of each state. So conventionally, we take a row vector called pi whose elements represents the probabilities of the state. Well, basically, pi denotes the probability distribution of the states. Suppose in the beginning we are on a pizza day. So the second element, which corresponds to the pizza, becomes 1 and other two remain 0. Now see what happens if we multiply the row vector with our transition matrix. We get the second row of the matrix. In other words, we get the future probabilities corresponding to the pizza's day. Then we take this result and put it in the place of pi 0. We will do this once again. Now, if there exists a stationary state, after a certain point, the output row vector should be exactly same as the input vector. Please denote the special row vector as pi. So we should be able to write pi a is equals to pi. If you have ever taken a course of linear algebra, then you should find this equation somewhat similar to a very famous equation. Yes, I'm talking about the eigenvector equation. Consider lambda equal to 1 and just reverse the order of multiplication and you have got our equilibrium state equation. How to interpret this in the graph? Then we can imagine that pi is a left eigenvector of matrix A with eigenvalue of equal to 1. Now, the eigenvector must satisfy another condition. The elements of pi must add up to 1 because it denotes the probability distribution. So after solving these two equations, we get the stationary state as this. So it tells us that the restaurant will serve hamburger about 35% of the days, pizza about 21%, and hot dogs about 46%. Using this technique, we can actually see if there are more than one stationary states. Can you guess how? We just need to see if there exists more than one eigenvector with eigenvector equal to 1. Now let's compare this result with the previous one that we got from our simulation. Look how close they are. They kind of validate each other. So that ends up the application. By now, we expect that you have a very good understanding about the definition, the history, the properties, the types, and of course the applications of the Markov chain. Thank you for watching this video and we hope to see you again. Bye-bye!